Recording in progress.
Hello. Welcome to our final video on colligative properties of solutions, where we are looking at how to practice finding the osmotic pressure raising or the osmotic pressure of a solution based on its solute concentration. So practicing osmotic pressure raising. So here we have the osmotic pressure of a solution containing 5.87 milligrams of unknown protein per 10.0 milliliters of solution is 2.45 torr at room temperature. What is the molar mass of the protein? So I'm going to first off identify our goal. So our goal is to find a molar mass. And remember, molar mass is an intensive property. So as long as we can find a mole quantity, so moles of protein, and divide that by the mass in grams of protein, then we will be able to get that intensive property. Ooh, I have this backwards, grams per mole. So grams protein over moles protein. Point being, if we can solve for like each of these quantities that are extensive by themselves, then we can divide them and get the intensive molar mass. So this is our goal. We want grams per mole. Okay, problem, osmotic pressure of a solution. So let's see if we know anything about the osmotic pressure. Is 2.5 torr. 2.45 torr at room temperature. We presume that is 25 degrees C, which is 298.15 Kelvin. So we've added our 273.15 to do our conversion. Okay. We are talking about a protein here. This is very similar to our discussion of urea, right? We are assuming that this protein does not have any kind of like acidic nature, meaning we assume that this protein does not have any dissociation when it dissolves in solution whatsoever. So we are going to assume I is 1. Generally, if you are given something that is not an ionic compound, nor is it an acid or base, you can presume its I is 1. You can presume that it's a non-electrolyte. And we have our goal of finding grams of protein. So let's see here. Grams of protein, I know that I have 5.87 milligrams, or using my conversion factor, this is 5.87 times 10 to the negative 3 grams. You can prove that yourself. 1, 2, 3. So that would be 0.005 or 1, 2, 3, 10 to the negative 3 grams of our protein. So we have our numerator. And now we need to figure out the moles of protein. And let's see here. I was given 5.87 milligrams of protein per 10 mils of solution. So if I were going to find my molarity of solution, which is my moles of protein over liters of solution, I could at least fill in a part of this definition, right? Like I don't know the moles of my protein, but I do know the volume of solution. So that's 10.0 milliliters or 0.0100 liters of solution over X molarity. So let's maybe solve for our molarity and see if we can't get something from that. So solve for the X moles. All right. We've got our osmotic pressure equation. Pi is equal to mRTI. We need to ensure that R is something we know. Liter atmospheres per mole Kelvin. which means that our osmotic pressure needs to be converted into atmospheres. There are 760 torr per atmosphere. So if we take our 2.45 torr and divide by 760, we get a value of, let's see here, 3.224 times 10 to the 3 atmospheres. Okay, so I've got some information collected. Let's see if I can't maybe put it all together or even isolate this equation, like rearrange this equation to get what I want. Because the only thing that I know in this particular equation that has anything to do with moles of protein, which I need for my molar mass, is my molarity. So let's rearrange so that the molarity, that's pi over RTI. So pi, our osmotic pressure, is 3.22 carrying a 4 times 10 to the negative 3 atmospheres. That is over R, 0.08206 liter atmospheres per mole Kelvin, times T, 298.15 Kelvin. So we've got M molarity, that's equal to, let's at least get our denominator value. So 3.224 times 10 to the negative 3 atmospheres over 0.08206 times 298.15. This gives me 24.466. And let's think about our units here. Kelvin and per Kelvin, this is liter atmospheres over mole. And then atmosphere over atmosphere will cancel. So then we have our quotients. So 3.22, carrying that 4, so we don't have a rounding error that we're introducing. Okay, when I do this, and please check my work, I get 1.3177, let's call it that, 78 times 10 to the negative 4. And this will be, let's see here, 1 over liters per mole, or the reciprocal of that, which would be moles per liter. So we have our molarity in moles per liter. And we now want to solve for moles. So we know our volume, which is our 0.0100 liters. So then times 0.0100 liters. That'll change our order of magnitude to 10 to the negative 6. This is 1.3177 times 10 to the negative 6 moles of protein. So we have our moles of protein. Now we need to get our grams per mole. So our grams was 5.87. Oof, that's a blank slide. Let's go back. So molar mass, 5.87 times 10 to the negative 3 grams divided by 1.3177 times 10 to the negative 6 moles. So divide by our 5.8. There we go. Should get a pretty big number here. We would expect that. Proteins are pretty massive. Yeah, we get a 4.455 about, let's just call it that, grams per mole. This is the molar mass of our protein. Big, large molecule. Makes sense that it would be very large molar mass. Now you could have done this problem another way, meaning you could have plugged this straight into here and then multiply your volume over. So like instead of getting moles first, you could have done moles and already included your volume product. That's fine, whatever you need to solve the problem in a way that makes sense to you. But the idea is trying to ensure that our units are correct when trying to use our osmotic pressure equation so that we can solve for any of the components that are included in that equation. Okay, this wraps up our conversation about colligative properties. So coming up next is chemical equilibrium, which is a fantastic and I think really exciting conversation to have because it takes some things that we've learned in Gen Chem 1 and adds more detail and nuance to them so that we actually know the truth of what's happening in a chemical reaction, which I think is cool. So I will see you in our next topic of discussion, which is chemical equilibrium. Nice job with colligative properties.